Okay, so two solid steel marbles, one with a mass of 0.25, the other with a mass of 0.33, collide with one another in an elastic collision, so they conserve momentum and kinetic energy. If the 0.25 kilogram initially has a velocity of 1.3 towards the other, and the 0.33 one has a velocity of 1.5 towards the first, what are the velocities after the collision? So let's draw a little short diagram here just to kind of show what's happening. So here's my first marble. It has a mass of 0.25. It's going this way. It has a velocity of 1.3. The other one is going in the opposite direction. It has a mass of 0.33. It has a velocity of negative 1.5. Now, I know it doesn't say negative, but I know it's negative because it says it's going towards the other one, towards the first. So if they're going towards each other, one's got to be negative, one's got to be positive. And it doesn't matter which one, but one of them's got to be. Okay? After the collision, they bounce off each other, but we don't know what either one is doing. The 0.25 we know is going left, but we don't know how fast. We'll call this 1. And the 0.33 one is going to the right, but again, we don't know how fast. Okay, so knowns and unknowns. Object 1 will be the first ball, so the first steel ball, M1, has a mass of 0.25. We know that before it collides, it has an initial velocity of 1.3 meters per second. And after the collision, we don't know what its velocity is, so we'll just call it V final, question mark. Object 2 will be the other one, mass of 0.33, initial of 2, negative 1.5, and the final velocity of 2 we don't know. All right, so step 1, do all your knowns and unknowns like you're used to doing. All right, step 2. The next step in this problem is we need to conserve momentum, because objects that are in elastic collisions conserve momentum. Okay, so remember, the way you conserve momentum is the momentum of object 1 initial plus the momentum of object 2 initial equals the momentum of object 1 final plus the momentum of object 2 final. Now, in order to save a little bit of time here, I'm going to go ahead and set up the whole equation just in one go here. So remember, P equals mv. So all I'm going to do is a whole bunch of P equals mv's. So here we go. First P equals mv is the initial for 1. So mass times the initial for 1. So that is 0.25 times 1.3. Okay, that is a value of 0.325. Okay, plus the momentum of object 2 initial, so that's 0.33 times negative 1.5. And when you multiply that together, you get negative 0.495. Okay, final momentum of 1, mass times final velocity. So since I don't know what the velocity is, I'll just call it 0.25 v final for 1. And final momentum of 2, I don't know what that one is either, so it's just 0.33 times v final 2. Okay, you cannot combine these two. We did that before because they stuck together. If they don't stick together, you cannot combine them, so don't. All right, and let's go ahead and simplify this down as much as we can. 0.325 plus a negative 0.495 is going to be negative 0.17 equals 0.25 V1 final plus 0.33 V2 final. I cannot do any more with that. I cannot solve this any more than it's already solved. That is as much as I can do. So we go on to step 3. So we did knowns and unknowns. We conserve momentum. Now we need to conserve kinetic energy. See, if you remember back to math, you'll remember that in order to solve two variables, you need two equations. So here's my first equation, conservation momentum. Here's my second equation, conservation of kinetic energy. So the kinetic energy of 1 initial plus the kinetic energy of 2 initial equals the kinetic energy of 1 final plus the kinetic energy of 2 final. And remember, kinetic energy is 1/2 mv squared. So ostensibly, we would do the exact same thing we did above, just with different numbers here. And that seems fine, but it's going to get absurdly nasty. Like, it's just going to get gross. This is 1/2 mv squared, 1/2 mv squared, 1/2 mv squared, 1/2 mv squared. You're going to have to substitute into a squared. It's going to get gross. So, I'm here to save the day. Okay? I'm not here to make it worse. I'm here to make it better. Here's how I'm going to save the day. I'm going to give you a shortcut equation. And guess what? You can use it every time. In fact, you never have to set this up. Never. You don't ever have to do it. You can use the shortcut equation instead. And you're probably saying like, oh, wow, so I bet this is physics shortcut, so it's probably like you can leave off one of the kinetics. No, no, no. Don't be so pessimistic. Here we go. Ready? Here's the shortcut equation. V1 initial plus V2 initial equals, oh, sorry. Too many initials. V1 initial plus V1 final, V2 initial plus V2 final. That's it. That's the whole equation. See? Look how much better that is. So, when I say conserve kinetic energy, I mean do this. So, let's go ahead and do that. So, the initial of 1 is 1.3. Plus the final of 1, I don't know what it is. Equals the initial of 2, negative 1.5. Plus the final of 2. There you go. Now we have two equations. Okay? Here's equation 1. Here's equation 2. So, I need to solve for either V1 final or V2 final. It does not matter which one. It doesn't matter. Doesn't matter. I like to make my numbers stay positive, so I'm going to add 1.5 to both sides. When I do that, I get 2.8 plus V1 final equals V2 final. All right. So what I did is I figured out what does V2 final have to be. V2 final has to be whatever 2.8 more than V1 final is. I don't know what it is, but if V1 final is 1, then V2 final is 3.8. It has to be 2.8 more than whatever this is. So, if you remember substitution, you know what's coming next. If you don't remember substitution, that's okay. I'm going to show you. I am going to take this value for 2.8 plus V1 final. I'm going to put that instead of V2 final up here. So I'm going to go up to equation 1, and I'm going to take what I got from equation 2 and put it in that spot instead. So this right here, 2.8 V1 final, it's going up here. It's going to go in here. And I'm going to write that down here now. Step 4. Substitute. So I'm going to write this equation again. Okay, I'm using equation 1 again, just so we know which one I'm using. Okay, negative 0.017 equals 0.25 V1 final. So far, so good. Plus 0.33. Here's where we're going to change something. I'm not writing V2 final. I'm going to write what V2 final is. It is 2.8 plus V1 final. And now we're going to do your favorite mathematical thing. We're going to distribute 0.33 times this, 0.33 times that. Okay, that's going to give me negative 0.17 equals 0.25 V1 final plus. So 0.33 times 2.8 is, oh my gosh, if only I could write clearly. There we go, 0.924. And 0.33 times V1 final is 0.33 V1 final. And now look what we got. V1 final, V1 final. These we can combine together. So let's do that. Let's get all the things together. Let's get all the numbers to the other side. Minus 0.924, minus 0.924. Let's combine the two V1 finals. When I do that, I get the following. Negative 1.094 equals 0.58 V1 finals. I can add these two numbers because they both have x with them. Okay, V1 final, but x. And I can combine these two together because they're both numbers. So now I've got this. I'm going to divide both sides by 0.58. And I get my answer, V1 final equals negative 1.89. And you're probably saying to yourself, I bet we're not done. Hey, we're not done. No. You guys are figuring it out. Good job. But we're very close to being done. Now that I know what V1 final is, plug it back into equation 2. Yep, I snaked it. I have a little bit of space left. Oh, and I have almost 2 minutes left. Oh, we're going to make it. Okay, so last up, solve for other. And don't go back to this equation. I mean, yeah, this would work, but don't go back to this. Go back to the easy one. Go back to the one where it's already solved out. So 2.8 plus negative 1.89 equals V2 final. So V2 final equals 0.91. Yep. Let's see if those answers make sense. So this has to conserve momentum and energy, kinetic energy specifically. So this object started with less energy because it's going slower and it has less mass. This one is going to have more energy. So after the collision, does my first object end up with more energy in the opposite direction? Yeah, it sure seems to, right? It's going faster and in the opposite direction. What about this one? It's going slower and in the positive direction. So from what we have, those numbers make sense from our work.